Hello and welcome to lesson 4.2. This is impulse. It's our second lesson in the momentum chapter. We'll dive straight in with the definition for impulse. What does this mean? What the heck is impulse? Impulse is the product of, I'll put this next word in parentheses, average force and time. So if a baseball strikes a wall, for example, it's the amount of time that that baseball is in contact with the wall and the amount of force that the ball is being pushed with. So impulse is very important when it comes to collisions, things that are making contact and causing change to one another. This is not enough for me. This definition is a little, mathematical. So another way to put it is, it is the change in an object's momentum. Whoa, glitching a little bit. Okay. So both of these actually represent equations. We'll break them down pretty thoroughly here. First, as it says, impulse is just the product of average force and time. For impulse, we'll use the letter capital J. It's equal to average force times the amount of time that it's in contact with the wall. Technically, impulse and force are both vector values, so we would put little harpoons on the top if we wanted to be fancy. In fact, I'll do that now. But these are not super important for this class. It's just to show that, hey, when you get this answer, you need to have a plus sign or a minus sign with it. Let's break them down. Like I said, this is impulse. Since it's change in momentum, the unit for it is kilogram meter per second. But also, if we look at the equation, check it out. We have force times time. The unit for force is N. The unit for time is S, newtons seconds. So impulse can also have the unit of newtons times seconds. But really, they mean the same thing. Here's why. This is, like I said, average force. And it has two units as well that we kind of forget. It's capital N, or it actually has another unit. It's kilogram meter per second squared. So really, capital N is a shorthand way of writing kilogram meter per second squared. And so that's why this has two ways of being written, just like force has a unit with two ways of being written. These mean literally the same exact thing. These mean literally the same exact thing. It's just two ways of writing it. Different languages, if you will. And of course, this is time, but I think we should emphasize that it is time in contact, measured in seconds. So this is, again, for like collisions, things that strike one another. They'll be in contact for a finite amount of time, even though it doesn't look like it. When I move my camera, no, we're good here. So let's talk a little bit more about this average force. Why is it average? To do that, we'll consider a baseball striking a wall. So when a baseball strikes a wall, it doesn't just hit the wall and turn around instantly. It doesn't happen over 0 seconds. I'll try to draw like a cartoon of it. So if the baseball is moving to the right, here's the wall. The baseball will make contact. A moment later, it will start to squish down into like an egg shape. And if you slow down this motion with a camera, you'll see that the baseball almost entirely flattens out. I'll see if I can bring a video like that to our class, to our Zoom meeting. So the baseball will crunch down, deform to almost like a pancake, and then it'll go back in the other direction. So this is called elastic energy. It stores its energy as elastic energy. And then as it expands again, it'll almost show this same picture. So it's like going right to left and then left to right and then right to left. It'll crunch down and then it'll expand again and go flying to the left. The point here is not only is it in contact with the wall for a time greater than 0 seconds, but also the force is going to change during this time. So the force diagram, if you will, would look like this. The amount of force based on time. So at first, there's no contact with the wall, so there's going to be 0 force. It'll begin its contact with the wall, and as it crunches down, the force will get greater and greater. And it's a very imperfect change. Lots of complicated physics that occurs as it crunches down. Physics that we won't go over in this class. But what's quite cool here is to see how it changes. So we have an increasing force and then it decreases again. Those of you in calculus class might be able to calculate this area. But the important thing is that somewhere down here is the average of all these little pieces of force. F bar, F average. Another cool concept is the graphing techniques that one could use here. If we were to calculate the area of this, think about what we would have to do. We would take the base of this, which is time, times the height of it, which would be force, and look at that. Base times height, I guess it looks like a triangle, maybe 1/2 base times height. The important thing is we have force times time. So the area of that graph down there is J. So this is just a cool concept. I just want to show you that graphs have meaning. The parts of graphs have meaning. So the area of a FT diagram, a force time diagram, represents impulse. Much like the area of a acceleration time diagram. No, we used velocity time. The area of a velocity time graph is displacement. Check out your graphing chapter if you're not sure where that's coming from. Okay, so just a cool concept there. I might give you some graphs and ask you to calculate the area of the graph. What you have to remember is that this right here, area of a force time diagram, represents impulse. Memorize that. So if I give you a graph and say, what's the impulse in this situation? You should be able to calculate area. Up here in our equation, of course, I say average force. In this class, with word problems and such, every force that I give you is actually an average force. So as far as average force goes, you don't really need to be concerned with that. The main concern is be able to calculate area of a graph. If that's on a quiz or something, I'll give you examples during class. So here we go. How do you use this equation? Here it is. We'll do an example to demonstrate it. Another baseball problem. Baseball begins moving southward with a velocity of 38 meters per second. Baseball begins moving southward with a velocity of 38 meters per second. It makes 0.0016 seconds of contact with a bat and then moves northward with a velocity of 58 meters per second. And part A will be calculate the impulse. Applied to the ball. Okay. A baseball begins moving southward with a velocity of 38. It makes 0.0016 seconds of contact with a bat and then moves northward with a velocity of 58 meters per second. Calculate the impulse applied to the ball. Quite easy to break down, I hope. We're looking for J. Notice I've dropped the harpoon because it's really not that important. They give us a velocity of 38 meters per second, but that's south. So it's negative 38 meters per second. We have a final velocity of positive 58 meters per second. And T is 0.0016 seconds. So what the heck is going on here? I'm supposed to calculate J, but when I go to look at my equation for J, there's no velocity involved. It's all about this right here, though. It's change in momentum. J is the same thing as delta P. If you still have space, go ahead and write that here. If not, write it in your margin. Impulse is change in momentum. We already learned about that concept. J is delta P. Delta P is something we learned last lesson. What this definition is saying is that, okay, impulse and change in momentum are virtually the same thing. We just give impulse a special name because it has special uses when it comes to force. So, really what they're asking us for here is change in momentum. That's a hugely important concept to understand, that impulse and change in momentum are the same thing. So when they ask you to calculate impulse, keep those older equations in mind. Here's our equation for change in momentum. We're going to need a mass for this object. Hold up. We're going to need a mass for this baseball. So I forgot to write a mass in this problem. We'll go ahead and do that now. M is 0.62 kilograms. My apologies there. I should have that included in the beginning. It's supposed to be a 0.62 kilogram baseball. So when I break this equation down further, I'll have mass in it. That's how I saw that there was a mistake there. So it's MVF minus MVO. From there, I can plug my numbers straight in. Delta P equals 0.62 times 58 minus 0.62 times negative 38. Set up nicely that we can plug it all into our calculator at once. 0.62 times 58 minus 0.62 times negative 38. That's how I have it in my calculator if you want to compare. Oop, I've made a mistake here, 0.62. So it'll be 46.6 kilogram meters per second. You could technically just circle that answer because they mean the same thing. I'm going to write it the official way. They've asked me for impulse, which is J. Delta P is change in momentum. But like I said, they're the same thing. 46.6 kilogram meters per second. This unit could also be newtons times seconds. So there you have it. Calculate impulse applied to the ball. We didn't even use our new equation, but we will in the next one. Part B is calculate the force. Calculate the force applied to the baseball. You know what, I should technically say average force. But in this class, average force and regular old force are going to be the same thing. We won't have varying forces in this class. Calculate average force applied to the ball. Quite easy based on what was given. Remember, we have J, we do have J now. We have T, and we have, well, that's all we really need. J equals F times T. There's the new equation of the day. Technically, there's a bar up there, but you can skip it if you wish. I'll solve symbolically just because it's cooler that way. We'll divide by T on both sides. So the average force is the impulse over the time. And so it'll be 46.6 over 0.0016. Notice how small the time is. That very small amount of time will create a very large force. 29125 newtons, a tremendous amount of force. But it only happens for a split second. Okay. So I'll close this lesson with just a little bit more about the equation. I think it's pretty easy to use, as we've seen here. But where does this equation come from? Physicists don't just make this stuff up. They don't conjure it out of thin air. Most physicists just take their stuff back to Isaac Newton. So almost, they say all roads lead to home. All physics leads to Isaac Newton. And here we'll start with Isaac Newton. Isaac Newton famously said in his second law that the force acting on something is equal to the mass of that object times the acceleration of that object. What we know about acceleration is that by definition, it is the change in velocity of that object divided by the time of that change. So we'll plug that in for A. F equals m times delta v over t. Just playing around with the equations. This is how most of physics is done, just making stuff up. Now I'll multiply both sides by t. Seems like something to do. Okay, so I have F times T equals M times delta V. Yo, what's going on with this here? Delta V. I know another way to write delta V. It's written like this. VF minus VO. In algebra, they do this thing called distribution sometimes. I'll try that. MVF minus MVO. Maybe you can see what's going to happen here, maybe not. We're just playing. What's another way to write this? Well, this is the final momentum of the object. And this is the initial momentum of the object. And there it is. PF minus PO is delta V, delta P. And here is our equation. Delta P is also written like as J. And so here's the equation that we originally started this lesson with. Really, it was written J equals FT, so we could write it like that. But here's where it comes from. So the special thing about this equation is all about time. The less time that something spends in contact with another object, the more force there will be. This value is constant for something that slows and stops. So we'll probably have to, this video is getting a little long, so we'll probably have to talk later. But basically, the equation implies this. More time means less force. If you jump into a fluffy bed, the time of your collision is very large. Therefore, there's less force pressing on your face. If you jump onto a concrete slab, the time that you're in contact with the ground is very, very small. So when you hit your head on the concrete, there's a very small amount of time that contact occurs, and therefore it has a large force. And that is the main thing that the main application of this, very important with car accidents and car safety, which hopefully we'll get into. Don't worry so much about this derivation. It's just, that's just fun. More important is to remember that and to remember that J equals delta P. Thanks for watching. I'll talk to y'all soon.